So hello, we are going to talk about the capacitance, which is chapter 8. So capacitance, in a sense, it is basically it is composed of the two conducting plate, and then one side is a plus charge, and the other side is negative charge. And then sometimes you can put some dielectric in between, which is characterized by the dielectric constant kappa. Okay. And then usually it is charged by battery. And then what we need to do is that how the electric field is going to be confined. So if you look at this part, then you'll see that electric field is confined only in this space. It is constant. And outside is zero, left side is also zero. The only non-zero electric field is within these two plates. So that's the beauty of capacitance. And then this capacitance is characterized by the capacitance C, and then it is related is Q times V. So if you have a high capacitance, that means you can store a lot of charges, and also you can connect it to the high voltage. Okay. So that means if you have a certain capacitance, you can store the electric field energy here. And electric field energy. And it's time to think about, um, I'm sorry, this should be divided by. Okay. And then we are going to look at some of the basic configurations. So this is the planar, and then we have seen that there's a concentric spheres minus Q, or sometimes it's concentric cylinders, etc. Okay, let's try to look at what we can solve, utilize this. What voltage must be applied to an 8 nanofarad capacitor to store 0.16 millicoulomb of charges? Okay, so you need to find out the voltage, which is unknown. And then there is a capacitor, C is given. And then there is a charge. Why is this? Okay, so capacitance is known, charge is known, and then the relationship between the charge and the capacitance is given by Q is C times B. So we can solve for the B. But the starting point here is that your capacitance is actually your charge divided by the voltage. Okay, that's important. In electromagnetics, it is important to keep the unit is a coulomb or volt is farad. Now try to think about a spherical conductor of a radius of 640 meter and calculate its capacitance. The constant kappa has a value of K. So we need to find out radius is given, Coulomb is given, and then as we have seen before, the electric for the conductor, if it is conductor, and note that we do not have a charge here. Charge is not known, but we have to find out C. Okay. That means C is given by Q over V, and then we need to find out the V, and then we assume that we are going to have a Q, okay? And then try to find out the electric potential V on the surface of the isolated conducting sphere. And then this is what we have done in the previous examples. And in this case is KQ over R. So in other words, in the conducting sphere, it looks like it's a kind of a center. At the center, all the charges are accumulated. And then by Gauss law. And note that it is equipotential. So anywhere on the conductor, it has the same potential. Here, 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 the same potential. And then we found out the potential is given for an arbitrary charge Q here. So please look at the logic. So in previous example here, we are given, let's say, charge, and then a charge and voltage, you can find out the capacitance, okay? So, but in this case, we are not given any charges at all. So we are going to assume there is a Q on the surface of a conductor. And then for that assumptions, we are going to find out this potential. And then C is given by this one, so that you see that Q will be canceled out. And then it is this number. Okay, so please look at how the logic is evolved. You assume the charge Q, and then for that charge Q, calculate the potential, and then using the capacitance definition. So note that this is the definition, and then from the definition, you can find out the capacitance. What is the energy stored in this capacitor of a hot defibrillator charged to this voltage? Okay. So note that in this case, the capacitance is known and the voltage is known, and then we need to find out energy. Okay. So relevant formula is given by this one. Okay. And then please look at how this is derived previously. So, but it starts from the small ue, which is E square for the electric field. And then electric field is determined by the capacitance and the voltage. And then you can derive from this one to this energy. And then this should be divided by the U. Capital U is small ue times voltage. And then note that in this case, we are given capacitance as well as the voltage. Then you can just plug in these numbers into the formula, and then you can get, the numbers, which is the energy. And then this is the typical, most common example of a capacitor problem. So you have two parallel plates with the area is given and D is given. This area and the D parameters is important to find out capacitance. Okay. And then it is filled up to parallel slab of a dielectric material of equal thickness. That means this spacing is filled by the D over 2 thickness kappa 1 on the top, D over thickness over D over 2 at the bottom half with the dielectric material with the kappa 2. And then what is the total capacitance? That's the we need to find out. So note that the area is known and spacing is known. Thickness of each slab is known. Dielectric constant is known. And then relevant formula is capacitance of a parallel plate capacitor with a dielectric is going to be like this. And then if you look at it closely, let's assume that it is charged to the plus Q and charged to the minus Q. Okay. And then note that the dielectric is composed of the dipole, so that its dipole should be aligned. In this way. And this is also true for okay, so you will have a and then you have a so let's do it once again, plus minus, plus minus. And I think I need to change the color. So for the kappa 2, so if you look at this minus plus, minus plus, so that you have a minus here. So it looks like what is going to happen here is that it is actually so it is composed of the two separate, just like here, you can have a plus and minus, so it is going to be canceled out. So you can assume that you have a plus Q, minus Q, minus Q, plus Q, minus Q, okay? And then obviously these two charges will cancel out so that the charge is conserved in this case. And then it looks like a kind of a C1, C2, okay? So it's a kind of a two parallel capacitor series in series, okay? So that you need to start from this. Two separate capacitor connected in series. That's the starting point. So each capacitor, we know the formula for the parallel plate capacitor. We know that this formula. So area, thickness, and your dielectric constant. Okay. And then we can calculate the C1 for copper 1 and C2 for the copper 2. And then note that it is serially connected, and then the total capacitance is going to be like this. Okay. And then you can have this total capacitance formula. Note that here thickness for each capacitor is now d over 2. But the area is the same. Okay, that's the big difference. And what about this? In this case, if you look at it, okay, so that there's a two dielectric, which is filling the surfaces serially in parallel. Okay, so that what it means is that if you have a area A, then it covers A over 2 area, A over 2 area, but with the same thickness. So if you look at it, the area is the same for this capacitor and this capacitor, but the thickness is halved, and then they are connected in parallel in series, and then in this case it is connected in parallel. C1, C2, okay. So plate area is going to be reduced to A over 2, half, but the spacing is the same, okay? And then we are going to utilize the same formula here for the slab capacitance. And then in the case of a parallel, the total capacitance is just simple addition. And then it is going to be addition of these two capacitor, and then you can find out total is given by this one. And then there is another problem. An air parallel plate capacitor with an area and distance is charged to certain voltage. What is the surface charge density on the positive plate of the capacitor? So note that we are to find out surface charge density. Okay, sigma. Let's try to find out what is given. The area is given, distance is given, voltage is given, and then we need to specify the capacitance. And then once we know the capacitance and then the total charge accumulated on this parallel plate, is Q minus Q, and is given by Q equal to C times B. And then our surface charge density is going to be Q divided by the surface area A, so that you can get the C is this one. And then we know what the capacitance is for the parallel plate. And then we can find out is this one. Okay. And alternatively, you can use the electric field for this case. This is this one. And then you note that this is the parallel plate conductor, and then you can find out this one. And then from this, you can find out sigma is epsilon times E, right? And then E is B over D. Okay, either way, you can find out the solution. Consider a parallel plate capacitor, and dielectric layer is given. The capacitor charged to a certain voltage. The charged capacitor is first unplugged from the power source, and then the dielectric layer is pulled out. It's a little bit complicated. First of all, the parallel plate capacitor is charged, and then your voltage is disconnected. Okay, so there is no charging mechanism here. Okay, so that the only conservative is that the charge on those plate. And then in this case is you're going to put the dielectric pulled out. And then we need to find out the potential difference between the plates of the capacitor. How is going to change? Okay, so plate separation, dielectric constant, and thickness, initial voltage is given. And then the condition is important. You need to realize what does it mean by it's disconnected. Okay, that means capacitor is isolated, unplugged, so that charge is constant. Okay, so if you think about it, C is Q over V. Okay, and then we need to think about how the initial charge and the final charge would be changed. So that Qi is Ci times Vi. And then Qf is Cf times Vf. So note that Qi should be equal to Qf. But what was buried was that capacitance is changed. So initially it is filled with copper, and now it is filled with air. Okay, so that initially it is a Vi, and then we should have a Vf. Okay, that's the C. That's the case. This is the Ci, and this is the Cf. Okay. So here is the case. Note that only the part of the capacitance is filled. Note that D is 10 millimeters, dielectric thickness is 9.3 millimeters. So there is a certain gap, okay? And then the symmetry acts like two capacitors in series. That's what we have seen before. It is, if you look at it furthermore, then there is a kappa equal to 1, the kappa. And that's what we have seen before, right? So it is kind of a C1, C2 in series. And then we have seen this before, and so initially it is composed of the two material, air and dielectric. And then in the final capacitance, we are only air, and then that is given by this one. Okay? And we need to apply charge conservations. And then the initial charge should be the same as the final charge, so that we get this equation here. And then from this relationship, we get this one. And we know what the initial capacitance and what the final capacitance is, then you can find out this one, okay? So we can find out the voltage has been increased, okay, by plugging out the dielectric. So in other words, if you plug in the dielectric, and then voltage will also drop. Okay, that's it for today. And then I hope you would have a good preparation for the exam one. And hopefully you could get a good grade in the exam one. Thank you.